Hi everyone, welcome back to my YouTube channel. And in my previous lecture, I just gave you a short synopsis about the energy balance equation and how to deal with the problem, how to construct the equation according to the problem. And today we are going to solve a full energy balance problem and a new one. So the main thing is that here, like not the mathematical issue, but the problem is how to imagine where the energy flows. That is the main concerning here. And these problems are very interesting. And again, I want to mention that I am not going to read out the question again. You can just pause the video and read out the question and understand each and every concerning points mentioned here. And you can try with your own to solve it. Okay, so now I am going to solve the question. I hope that you already read out the question. And now let's get start and yeah. So now we are first look at the system. We have an ice water storage tank, and here the heat pump is continuously removing the heat at 10 kilowatts. And at the same time, a solar system is adding 3.5 kilowatts of heat to the system, but only for 3.5 hours of period. Now I want to ask you that is this a steady state problem? Of course not, because the temperature and the phase, the both are changing with the time. So this is an unsteady energy balance. In my previous video, I already mentioned that the energy, everything is whenever it's changing with the time, that is the unsteady, and when it's not changing with the time, that is steady. So we know that something is not variable, that is the constant. So here the system is unsteady. So we can write out the system upon dt not equal 0 because the derivative of the constant term is not 0. Constant term is 0, but the variable term is not 0. So now we can construct a basic equation of the energy balance. Here inside of the system, we can look on kinetic energy, potential energy, and the thermal energy. Except thermal energy, nothing is mentioned here, like chemical or nuclear. Now we have to check that is kinetic or something related things mentioned here or not. I hope that you have find out there is no term related to the kinetic energy here, no movement, no motion, so it will be 0. And also there is no point about the potential energy here, so only the energy will be the thermal energy inside of the systems. And here I hope that you already have understood like what is our the main control system here. I am going to mark it. The main control system will be ice water storage tank system. So this is our main system. And now I am going to write it down the energy balance equation of unsteady state like with on the system. So work supply, heat supply, and the material transportation supply. So I hope that you have already checked out there is no work supply on the system. So that would be also 0. And there is no material transportation through the system. So that is also be 0. So here the system is actually closed system, and only in the closed system we know only energy can transfer throughout the system and surroundings, vice versa, but not the mass. And here the only energy is transferred as the mode of heat energy. So now if we are going to balancing it, then we can balance the thermal will be equal to heat energy. And here the heat energy is like coming inside of the system via solar thermal energy. So we can write out Q dot in, and it's absorbed, like this heat is leaving the system or absorbed by the heat pump. So heat is leaving the system, then we can write out Q dot out. So we can specifically write down Q dot in means uh, it is coming in via solar system, and heat is going out, that is via heat pump. So I can mention this thermal energy as the net heat interaction on the system. Then it will be Q dot solar minus Q dot heat pump. I hope that you remember from my previous video, I mentioned you if the heat is leaving the system, then we have to denote it minus Q. And remember this equation in your mind, keep this in your mind, we will use it again. That is the important equation. Yeah. Now let's get started to solve our very first problem here. We have covered up the general overview of our system here. So yeah, sorry. So here in our question, they have give me the assumptions. I hope you already read out. So now think this situation physically what is happening. This part is very crucial. I have a question for you. Like, does the water start freezing immediately at 10 degrees centigrade? Obviously not, because the water has to first cools down from 10 degrees centigrade to 0 degrees centigrade. So it is our first step, that is cooling of the water, sensible cooling you can say. And then at 0 degrees Celsius it will starts to freeze, like the water will starts freezing or ice will be starts forming. So at 0 degrees centigrade it will start freezing, or we can say freezing means that we have to remove our latent heat. These two steps are very, very important. If you missed out any of these two steps, then the energy balance will be wrong. Now let's calculate the energy. We have to just need to cool the water. We have to first solve these, like how to we can solve that to cool the water. So straightforward we can write out. We know the equation, the formula we know Q cool will be mass of the water and the specific heat capacity of the water at constant pressure and the temperature difference. And here they provided our mass of water and specific heat capacity and the temperature initial and the final. So temperature drop here will be T1 minus Tf. So you can convert it in Kelvin scale, because that will help you to calculate with our unit calculations. So 283.15 minus 273.15. We know that 0 degrees Celsius means 273.15 Kelvin. So then the temperature drop will be of 10 Kelvin. Now we can put it here. The mass of the water is 8422 and it's 4.2. The specific capacity and temperature drop is 10. We can write down the units beside here. Mass of the water is in kg, specific heat is of kilojoule per kg Kelvin, and the temperature drop is of Kelvin. Kg we can remove, Kelvin we can remove. Then if you calculate it, the cooling energy will be cooling heat energy will be 353,724 kilojoule. So we first solved the cooling energy, like cooling for the water, we have derived it. Now we have to find out the freezing energy. Then we will calculate the total energy. So the freezing energy will be, yeah, here is the main problem. I have a question for you. Like, do we use the full mass here? Obviously not, because they mentioned that 50% of the water mass has to be frozen. So we have to take the mass of the ice as half of mass of the water. So half of 8422, that will be 4211 kg. So now if you want to calculate the freezing energy, then it will be Q freeze. I am writing it down. It will be mass of the ice and the fusion heat capacity, or you can say the latent heat fusion of the ice, that is given as 333 kilojoule per kg. 4211 into 333 kg into kilojoule per kg. Kg remove, and if you calculate it, you will get 1402263 kilojoule. Remember, this is the freezing energy. Like after water coolings down at 0 degrees centigrade, then at this temperature it will start at, yeah, at 0 degrees Celsius it starts to from the ice, and the energy is Q freeze. So this much energy is required here to form the ice. Now, if you want to calculate the total energy, then we have to add both Q, Q of the cooling and Q of freeze. And if you add both, 353,724 plus 1402263, you will get 1755987 kilojoule of the total heat energy here. That is the tank must lose according to our question. That is the total heat energy. Now, according to our question, we have to calculate the time, that how many time interval it will freeze the 50% of the water mass. So it's a very crucial part here. And do you think that we can divide the energy directly by 10 kilowatt? Of course not, because the solar system works only for 3.5 hours, then it stops. So we have to split that time. First, we have to check when the solar system was on, what energy was associated with the system, and what was happening in the system, and how much times it takes. And then when the solar system is off, then what is happening in the system, we can calculate later. So first 3.5 hours, that is, we are going to calculate when the solar system is on, then the heat interaction will be Q dot of the solar supply and the heat pump taking out the remaining heat. So 10 minus 3.5, and it would be 6.5 kilowatt. So when the solar system was on, it was supplying 10 kilowatt of heat, and heat pump was absorbing the 3.5 kilowatt of heat, but for 3.5 hours. So if you want to calculate the, and we know here the energy and the power relation, like energy or power relation is like we can write out Q or W divided by T. Power is the rate of the energy. Rate means we are defining with how much capability, with how much time you can do the work. So here the energy removed, I am writing the heat energy removed at 3.5 hours with 6 point, like here the power is mentioned, so we can write out Q means power into time. So Q removed is 6.5 kilowatt and the time is for 3.5 hours. And now if we calculate it with the seconds, so multiply with 3600 seconds, then we can write out it will be equal 81,900 kilojoule. So this is the removed heat energy. Then the remaining energy will be Q remaining, and it will be of Q total minus the removed heat energy. So 1755987 kilojoule, and the removed energy is 81,900 kilojoule. So it will be total of 1674087 kilojoule of heat remaining inside of the system, like in our ice water storage tank. Now, at this moment, the solar system is off, and at this moment, the heat pump will absorb this remaining heat. So, this remaining heat will be absorbed when the solar power is off. So, now the next step is solar is off, like after 3.5 hours. That is our next step. So, at this moment, heat pump will be removes the energy at 10 kilojoule per second. So then the time will be taken. We know from this equation, we can write out time will be Q upon P. So here the Q is the Q remaining, and the time will be taken. I am writing out T1. So Q remaining upon the power rate is 10 kilojoule per second. Yeah. So Q remaining is 1674087 at the rate of 10 kilojoule per second. Kilojoule cancel, and it will be goes up, then it will be in second. And if you want to write it down in hour, then just divide it by 1 upon 3600 and you will get 46.5 hours. So to freeze the 50% of the water, the total time is taken for first 3.5 hours when the solar panel was off, and when the solar panel was on, solar was on, and the solar pod is off for next 3.5 hours. The time was taken, the energy removed for 46.5 hours. So total time required to freeze 50% of the water is 3.5 plus 46.5, that will be for 50 hours. That is the answer of the first part. And now we have to solve our next part that asks that at the constant power rate, like 3.5 kilowatt, how much time would we take when the heat pump is turned off? So in part B, the heat pump is off. Only solar is available here. So how much time it would take to melt? Yeah, melt the ice mass. So now we already have calculated the freezing energy, that is the ice energy, and at this moment ice will starts to melt. So we can write out Q melt will be, we already calculated 1402,263 kilojoule. So they again asked the time, how much time would take, and we know the relation between power and the energy and time. So in Q upon T will be the power, and here the power is mentioned as constant flow of the Q dot solar 3.5 kilowatt. So we can write out, we have to calculate the time. So time will be Q melt energy upon the power of the heat pump they mention in the form of Q dot Q dot heat pump is solar. So the time will be 1402,263 divided by 3.5 kilowatt kilojoule, and it's kilojoule upon second. Kilowatt means kilojoule upon second. So kilojoule cancelled, and the second will be go here. And if you want to convert it in hour, then divide it by 13600, and you will get triple 11.3 hours. I hope that you have understood. Just I want to recap the whole thing in short scenario. We used one energy balance equation here, and that is the unsteady state energy balance. We check on the system, in the system and on the system, and then balancing it, what is involving here. And we separated the cooling and the freezing steps. Then we handle the time dependent heat rates correctly. Thank you.